record now. Okay.
Recording in progress.
Okay. So again, if we have example 10, the airplane's going this direction. It's 330 bearing, which is actually 120 in this circle. We do in component form, we get that. Now for the wind, the direction goes 45 degrees. So in this case, we just get straight up just that, right? There's nothing really special about that one. 45 degrees. So let's do the wind. Let's do a different color for the wind. So the magnitude is 70. And times cosine. I'm sorry, say again, Thomas? No, because it said direction angle, not they didn't say bearing. Okay. Yeah, you see all the balloons there. Okay. Cosine 45, you should know is √2/2, right? Oh, hey, that is awesome. Hold on, I gotta take that.
You want to scoot in a little?
Hold on, I got
Hella good.
Thanks, it. Awesome. All right. Oh, my kids are gonna love these when I bring them home. I'll leave it right here for now.
It's your house. You gotta wear it.
I'm not gonna wear the house.
Come on. Do you have a house?
No, she's the house. No, we're no, on the sky. On the sky. Yes. Here. No, I'm not gonna. No, it's gonna be annoying. I'm not gonna wear it. Sorry. Okay. Maybe near the end I'll wear it. All right, so that's gonna be 35 √2 and 35 √2. That's the wind, right? I think I got that right. Cool. All right. So now what I'm going to do is I have to add these together. Because what is the question really asking me? Yeah, so let me get rid of all the other stuff here. Exactly, 100% correct. Because the question is really asking for the resultant vector. Okay, so the resultant speed and direction.
We have to like, can we give that in other form?
No, yes, we do. Yes.
Or like we have to.
Okay, so yes, guys, quiet, please. So what I want to do is I want to add these vectors together. So it's going to be negative 250. I'm doing orange in Spirit of Halloween. Hopefully you guys can read that. If not, I could adjust colors. And then 250 √3. Also plus 35 √2. Okay, so that's my resultant vector. Now, how do I get the speed? Now, in the interest of making the numbers pretty easy to deal with, I'm going to convert these to decimals. That's probably a good idea. So if I convert these to decimals, I should get, and just trust me, I'm just copying the notes, but you get that. And you get 482.510. So that's my resultant vector. I simply added them. I used a calculator. Yep, that's all I did. Because what's results? So if you think about what's happening, guys, take a look at this. Let's look at the wind again, right? Let's look at the wind. So here's the airplane. The airplane's blue. And let me draw this a little better. Let me make this vector. Let's use an arrow because they have an arrow feature here, right? That's smart, right? Okay, that's the wind. Okay. So that's the wind, that's the airplane. What I'm going to do is I'm going to take this wind and put it over here. Because think about what the airplane's doing, right? Now we're physically seeing it. Yeah, physics. Actually, I love physics a lot more than this class. But Because it's more practical, but I don't like all the lab stuff. Lab stuff's crazy. But here's the thing. The airplane does this, right? The airplane does this. The wind does this. So the wind's clearly pushing it a little bit closer to the y-axis, right? Is it going more in the northerly direction? Sure. It's being pushed more in the northerly direction, but now if the western direction of the airplane, the engine's going that way, or the wind's going that way, they actually counteract each other a little bit, right? So there's a little bit of balancing act. So the airplane ultimately is going to look like this. Ultimately, the airplane's going to, and so pilots obviously have to make adjustments, right? That's what they do when they're dealing with the weather. So that's the resultant vector, which makes sense. It's going a little bit to the left. Definitely more of a stronger direction here. So it's definitely more of a northerly direction, right? Now that I have my resultant vector, let's get the speed and direction. You can see why I like this problem because it has a lot of different things involved here. A lot of different components, no pun intended. This problem. Get it? Good. All right. So, but there's a lot of parts of the problem too. That's I did a dual meaning of the word. Anyway, so resultant speed is this. Negative 200.503 squared plus 482.510 squared rooted. And just trust me when I work it out, it's going to be 522.511 miles per hour. Because the wind's helping you, right? Right, the wind's helping us, so we should go a little faster. I mean, not that much faster, because 5 miles per hour, so it went an extra 22, because there's a bit of a balance between the east and west. But overall, we're going a little faster. And then for my direction, tan theta will be the horizontal over the vertical. Yeah, because what you're doing is you're finding this direction here. So it's like a right triangle, right? You're trying to find theta. So 42.510 over negative 200. So theta will be the inverse tan of it, which I'll just tell you right now what it is. Hold on a sec. I think it's because Sans key seems off. 482.51 divided by negative 200.503. Inverse tan of that. Switch to degree mode. Yeah, you get negative 67.435 degrees. Yeah, go ahead.
Do you want us to be like doing radian mode or degrees?
No, degrees.
I feel like you're swapping a lot or sometimes.
No, I haven't done radians at all.
Okay.
Yeah. This stuff, no vectors, we've not done radians.
So
But there's other parts we do radians for sure. But this I want degrees. But if you think, so yeah, so let me finish the problem. So what's going to happen is that the true angle, because you have the reference angle, you want to do 180 minus that, because that's be an adjustment, which will be 112.56 degrees. .565. And that makes sense because that's the direction we're going in, about roughly about 112 degrees. So David says, yeah, question.
That was
Okay, yeah.
So we're gonna give theta just in like regular terms of the unit circle, not
Yes.
bearing.
Right. Yeah, yeah, let's just do direction. Yeah, because if you give it bearings, it's kind of confusing. I mean, you can do it bearings if you want. You'd have to kind of forget that little sliver there and do 360 minus that little sliver. If you want to, you could. If I ask that question, well, it's actually not a bad question to ask, but you just have to be mindful of how you express the answer. So,
Right.
yeah, so that's a word problem that deals with vectors. And you can see why vectors are useful now, because it helps break down things into their components and then bring it back together at the end.
You have to memorize what bearing is, or you just-
I would tell you if I do, I'd tell you. I forget. I had to look it up, so, or I had to have it there. Yeah, because I forget. All right, so let's move on to the rest of the notes. Let's see how far we get with this. And we go to 11 o'clock. So let's see. Okay, complex numbers. You guys did complex numbers last year, imaginary numbers? Yes? Okay. And pun intended, these get more complex today because there's more. Go on, just to review, I is root -1, that's imaginary number. We're going to talk about multiplying and dividing complex numbers. We're going to find powers of complex numbers, and we're going to find roots of complex numbers. These are a little tricky, but let's do the basics just so you understand what's happening. And then we'll kind of get a little more advanced later on. Okay, first off, the complex plane. You guys may or may not know this, I don't know. The complex plane is like xy, but x represents real and y represents imaginary. So this is the real axis. So the y-axis is the imaginary axis. And the x-axis is real. So when you have -1 plus 3i, you just plot this. If you have -2i, you plot this. If you have 4 minus 5i, you plot this. If you have -3, you plot this. Okay, take a moment to kind of just simmer on this a little bit. Just make sure you guys can make sense of it all. Where did I put my drinks? I had an iced tea drink. Why did I do that? Oh, that's fine. Appreciate it. Take care. Yeah, anyway, does that make sense? So this is like x and that's like y. If you don't see a real number, what do you assume x is? Yeah. You don't see imaginary numbers, what do you assume y is? That's called the complex plane. So there's a lot of analogies with this in x and y, right? It's very analogous to what we've been doing previous, like cosines x, sines y, you know, I and j vectors is x and y. Same thing here. So there's a lot of kind of crossover with the stuff. Okay, absolute value of complex numbers. That was it's kind of weird. Like, how do you take absolute value of like -1 plus 3i? How do you do that? Well, let's before I show you that, let's look at a, for example. Let me get rid of the other dots here. Okay, what is absolute value at its core? What does it mean? Like when you learn about absolute value in middle school, how is that defined for you guys? From zero, good, on a number line. But a number line is one dimensional, right? This is clearly two dimensional. So what's analogous to zero on a coordinate plane? The origin. And if absolute value is a distance from zero on a number line, wouldn't absolute value be a distance from the origin on a number line, right? So if I want to find that distance, so that's what absolute value is. It's just going to be the distance from the origin. Well, how would I find that length? What would I do? There you go, done. That's all you do. That's it. It's that simple. So get used to these letters. And there's a lot of letters I'm throwing away. Z is typically what we use to encapsulate a complex number. So Z equals A plus BI. A is the real component. Components again. BI is the imaginary component or imaginary part. So you can rewrite it. You can express the absolute value like this. A squared plus B squared rooted. That's it. That's all I do. Some people write like this. If you so desire. I mean, it is absolute value symbol, but mechanically you're just squaring A and B, adding square rooting. So for point A, that would be this, right? Which course is what? Root 10. And the other one, exactly, you do. Yes, you do. Because you're looking at B. B is a coefficient of I. Actually, I'm glad you brought that up. Because that would change things dramatically. Because remember, I squared is -1, right? So right, you totally neglect the I. Focus on the coefficient of I. Correct. Cool. All's good. Right. Okay, now let's start bringing some trig into the mix here. Okay, this is kind of a big deal. This kind of opens up kind of a big gateway here. Let's say I plot a plus bi. Okay. If you think about it, wouldn't cosine theta equal a over r? And wouldn't sine theta equal b over r? So wouldn't
We're just like using R.
exactly. Let's say a is r cos theta, b is r sine theta. Well, doesn't a squared plus b squared equal r squared? Yeah. Okay. So if I think about it, r is roots and also isn't theta going to be or tan theta equal b over a? Say it, go ahead.
The opposite value also,
Not necessarily. I mean, yes, it's a positive value. But here's the deal. If a equals r cos theta, then I can write this as r cos theta. But yes, r will be a positive value. You're 100% correct. If our a value is ever negative, it's gonna be because of the cosine. If our imaginary number is ever negative, that's because of the sine theta. But the r value, yes, is always a positive value. So I can factor out the r. So if you think about it again, a, because cosine theta is over r, so a is r cos theta. Sine theta is b over r, so b is r sine theta. We know this to be true. This is the magnitude. So that would, that gets me the length. But bottom line is this: a plus bi, r cos theta plus r sine theta I, or factor out the r. So this is the trig method form of complex number. All complex numbers can be expressed this way. Where you figure out what r is, which is that, figure out what theta is, which is tangent, and you can express it that way. So, for example, and we'll do an example in just a moment for example 3. You'll see how that works. But that's how you do it. So z is what we use to, again, encapsulate a complex number. So z equals r parentheses cos theta plus I sine theta. Where again, a is this. So I'm just repeating myself, obviously. B is this. R is this. And tan theta is this. Kind of some funny terms. I don't really use these terms, but just so you're not confused if a math professor brings this up down the road. R is the modulus of z. Okay, whatever. Theta is the argument of z, whatever. But we are going to talk about polar form. Usually I do this topic after I do the polar unit. I have to clear I'm doing it before, but it'll make the polar unit, I think, that much easier. But polar form is you put cosine with x, sine with y. There are infinitely many choices for theta, clearly, because you can go around the circle many times. So the trig form of a complex number is not unique, just so you know. But what if I restrict theta between 0 and 2 pi? in radians. I know I'm going back and forth. Vectors we did degrees, now we're doing radians. Adam, you are correct. We do go back and forth a little bit. Let's take a look at example 3. So you kind of make more sense of this. Okay, 1 minus I root 3. What quadrant is that in, by the way? 1 for the real number, negative root 3 for the you're in Q4. So I expect my angle to be in Q4. Okay, so what I'm going to do is figure out R is. R is going to be the square root of 1 squared plus negative root 3 squared, which should just be 2 straight out. Okay, theta is the inverse tan of what? Negative root 3, right? Which I think is going to be negative 60 degrees. No, wait, why am I doing negative? No, it should be negative 5. No, it's negative pi over 3. Yeah, no, we got it. Yeah, because you're doing y over x, right? But since you want it in here, what are you going to say instead? Pi over 3. So I'm going to express I know I'm out of space here. So I'm going to express my answer like this. Z equals 2 parentheses cosine 5 pi over 3 plus I sine 5 pi over 3. The 2's on the outside. So think about it. Cosine 5 pi over 3 is half. 2 times half is 1. Sine 5 pi over 3 is negative root 3 of 2. 2 times that is negative root 3. Now, why am I doing this? Like, that seems crazy. Why not just, like, well, what's the whole point of this? It's something neat that we can do. It's nice. But the real reason why we're doing this is that when we start multiplying or dividing complex numbers, or we start raising complex numbers to higher powers, or taking roots of complex numbers, that's going to be awfully hard to do with a complex number itself. It's much easier to do when you switch it to trig form. Just like with the vectors, when you break in component form, it's the same exact thing. We want to break this down to trigonometric components. So if I say like just to show you kind of like just blast ahead in these notes here. Let's say I want to do this. You can boil that 3 times, but if I change that to trig form, there's a quick and easy way to get that done by switching to trig form. So it's to make things more efficient as you get to these more advanced problems. Or look at example 8. That's crazy. I'm not going to FOIL that 5 times. That's ridiculous. But if I could switch it to trig form, it's going to be much easier to do that because there's a formula that goes with it. Or let's say I want to find like let's look at this here. I want to find the cube root of -2 plus 2i. That's crazy. I don't know how I even do that without switching to trig form. So again, it's going to make things much easier. So that's why we're doing that. Yes, go, David. And likewise with multiplying as well. It's going to be much easier. So let's look at part B now. Actually, why don't you guys try part B on your own? And also while you're at it, go and try example 4 as well. I think you guys can handle both. And I'll show you my answers in just a moment. Yeah, we're going to do part B of example 3 and also do example 4. I'm going to freeze my screen. You definitely need a calculator to do the angle. You definitely need a calculator.
Which one are more negative four? I need theta, I guess.
Degrees. 53.12. So, yeah.
Okay, so hopefully you see R is 5 to B. A squared plus B squared rooted, right? Pretty easy. Theta, I did the inverse tan of 4/3, which should be 0.927. However, that's in the first quadrant. I gotta be in what quadrant here? Q, 3. So I gotta make an adjustment adding 180 or adding pi radians. That's why I have pi to 0.927. And then I just write it like that. There we go.
Yeah, what is? Are you reading it or?
Gotta be radians. Gotta be radians.
No.
That's just there, right? Now we're in.
Yeah.
I know.
Are these only ever?
You can do it, it's rare you do degrees. It's rare.
Are you
Exam
gonna-
4.
Um,
That's just for Tom's question about example 3.
Oh, so why do you add pi? Mr. Band did it.
Because we have in Q3. That's in Q1.
Why?
No, we did.
Because of where your complex numbers. What that is.
Can you just move it over?
No, he used.
Because the thing is that this location is pointing in Q3.
Right.
So when you do the inverse tan of 4/3, that's 0.927. That's in the first quadrant. I want to be the third quadrant. How do you justify adding 180?
You
Right.
can only add, you can only add 180 at 360.
Well, it depends where you want to be. I mean, it depends on the referencing.
So you can just move it wherever you want.
We'll have to move to where we need to be. No, wherever I want.
Yeah, but.
Okay, let's back up a little, guys. Okay, let's back up here. Let's say I got. Okay, so you have this, right? Okay, where's that point? Where's that dot going to be? Okay, yeah, I know I'm rushing things, so let's. You guys are asking good questions, so. Okay. That's what I need, right? Okay, so if I do the tan theta equals -4/-3, which reduces to 4/3 anyway. So theta is the inverse tan of 4/3. If I punch in the calculator, it's going to say 0.927. But what does that really mean? That's actually in the first quadrant. Okay. That's in the first quadrant. Yes, go ahead, Kyle. So if that's in the first quadrant, that means that the reference angle here is 0.927. Okay. That's a reference angle. But I did a half revolution before I got there. What's half revolution in radians? I'm not choosing whatever I want. I'm doing it based upon what's appropriate. Based on the location. That's why I did pi plus that. Okay, Kieran, then Zaid, yeah.
Yeah. -1/2,
Exactly. Oh, wait. I'm losing my mind. I'm sorry, guys.
Yeah.
Thank you. My apologies. My apologies. Thank you. Yes, there you go. Thank you for catching that. Good. Yeah, same thing, Zaid.
No.
Cool. Great. Okay. Yeah, my apologies. See, I'm human. I make mistakes. It happens. So, we're good? No, not good. Okay, take your time. Yeah, for 4, 4, you just have to dive straight up. That's all. There's nothing special there. Just that unit circle. Unit circle. I just made a mistake. I simplified root 8 to mean 2 root 2. Okay, let's keep moving. I think we can get a lot done. I know I'm very ambitious here, but I think we can get a lot done here. Okay, so let's say I'm multiplying. Okay, let's take a look at example 5, guys. Now, example 5. Before I do example 5, I just want to before I talk about this stuff above example 5, let me talk about example 5. So example 5, you have 2 complex numbers, right? Z1 and Z2. Now, of course, if I work this out, I know that's going to be like, negative half and root 3 of 2, and I think that's root 3 of 2, and that's negative half. And of course, I can just write this in a plus bi form, and of course, I can multiply them like I usually do. But we can also do this in trig form. And there's a form that goes with it. So let's say Z1 is that in general terms, and Z2 is that in general terms. So if I were to actually go through the proof of this, C1, so these are not in your notes?
Yeah, sorry, it's not called example 5.
Okay. So if I were to multiply this out, I'm basically multiplying R1 and R2. And of course, I have cosine theta 1 plus I sine theta 1. Cosine theta 2 and I sine theta 2. And I'm kind of debating if I want to show the full proof. I trust you guys know how to FOIL stuff, right? Okay. Actually, no, that's a good proof. Let's do it. Okay, so if I FOIL, I have still R1, R2 on the outside, right? Okay, when you FOIL, what's going to happen? You got to multiply these together, right? You got to multiply these together. You got to multiply these together. Kind of see where I'm going with this, right? It's kind of crazy. So far, so good. And then plus I sine theta cosine theta 2.
Here we don't remove lines.
Oh, why would I ignore them? That was vectors. And that was a notation thing. This is an imaginary number. That's what you're thinking. I sine theta 2 cosine theta 1 plus I squared, which would be -1, of course. That is correct. Sine theta 1 sine theta 2. Okay. Whew. It's a lot. It's a lot going on there. Now, what if I do a little rearrangement? Okay. Do you guys see what I did? Well, tricky. It's I squared. So it goes over here. And you have see that both of them eyes. Okay, pulled it out. Pull out an eye for both of these, and I got it. Let me highlight. Highlighters are good. So you guys see exactly what I just did.
Well, we're doing.
It's going to end up flipping sometimes.
No, not really. Not kidding. Yeah, it does. I'm just kidding. It does. It simplifies actually really nicely. Do you guys see how I move things around a little bit? Okay. Yes, it does simplify. It actually simplifies in a very lovely way. It's a very beautiful proof.
We're gonna have to prove this.
I'll make you do it, not everyone else.
This is a Mr. Bag. Remember the Mr. Bag? Prove quadratic. That was impossible.
That's not hard quad form.
Well, not that, it was like something,
It's probably quad form.
it was something so neat.
Oh, he had
Okay, hold on, guys.
never got a single point that entire year for like.
Wait,
describing-
Mr. You know
Okay.
Gauch Jordan, right?
How did
You know,
Jordan?
Hold on,
Mr. Van gave us 12 minutes to do 3 Gauch Jordan.
Oh, that's crazy. That's So,
Like 7 minutes.
How did you factor out the off?
yeah, this sort of
Dude, and then,
Oh, yeah,
of course, on those
yeah.
Gauch Jordan.
How did you factor out the off?
Okay, so the things that, guys, quiet please. So I got two expressions, right? Here and here. These two in the middle. So I just pull an I out from both of these. Sine theta 1 cos theta 2, sine theta 2 cos theta 1. And then you just move that. I move this over here. Sound good. I squared it 1. Negative 1. I squared negative 1. Okay, Zay, go ahead.
Did you go from, cosine theta 1, cosine theta 2 minus sine theta 1? Is that because of the double angle?
Yes, good. Yes, thank you, Zay. Okay, not double angle,
Or some
form, yeah. So what am I doing here, guys? This is back to old stuff. This is the sum formula. You guys remember this? Cosine theta 1 plus theta 2, or cosine A plus B, is that. This right here, that's told you, it's a beautiful proof. This right here is some formula again. Sine, cosine plus sine, cosine, we switch angles. That, yes, 100% correct. Good.
That's crazy.
So that's how you can multiply complex numbers.
So that's the simplest.
So dividing follows a very similar process. Yes. I'm gonna write again. Actually, I'm gonna copy and paste, 'cause I don't want to write again. Okay, so let me move things around a little bit. Hold on a sec, guys. Okay, so I'm gonna copy and paste. Guys, stop talking. Or just focus, please. Thanks. Thanks, Lauren. Appreciate that. All right. So let me just readjust this. Oh, geez. There we go. Yeah, that works. Yeah, so that's Z1, Z2. Now, if I divide the two, I'm not going to do that proof because in the interest of time, I won't. But it's pretty similar. You do R1 over R2. And then you do cosine of theta 1 minus theta 2. Mine is when this is when Z1's over Z2. Plus I sine theta 1 minus theta 2. And the assumption that Z2 does not equal 0. That's the assumption. And by the way, if you punch this in your calculator, it'll do this for you. If you guys are curious where I is, second decimal point is where I is in the graphic calculator. It will actually do this for you. If you actually go through the process, it'll compute the answers for you very nicely. Okay. And I'm not going to get into powers and roots because that's a little too much. I'm going to do examples 5 and 6 and we'll wrap up the notes after that. We'll do powers and roots on Monday. And I should be able to wrap it up just fine. And then to start doing some review with you guys afterwards. So, all right. So let's look at example 5 and example 6. So it shouldn't be too bad. You don't need to actually evaluate this. If you want to find the product, you're simply going to do 2 times 8 times bracket, guys, quiet please, cosine of 2 pi over 3 plus 11 pi over 6 plus I sine 2 pi over 3 plus 11 pi over 6. Yes, of course. In terms of the formulas, I think I'd probably provide the formulas because I think it is kind of hard to memorize a lot of these. This is a very formula intensive unit, as you can tell. That I don't mind. But just want to make sure you guys apply it correctly. Well, let's go a little further. What's the LCD here? No, it's not. It's just 6, dude.
No, no, but I'm saying like. Then you're like, find that. Yeah. you can get it. Oh, yeah.
So it's 15 pi over 6. Well, it's 15 pi over 6.
5 or 2.
Cosine 5 pi over 2 is 0 because you go around once and you finish at 90 degrees. And of course, that's at 1. Final answer. 16i. 16i.
We don't turn back on.
We'll do one more in a moment, but ask questions.
Can we just turn it into 5 or 2? Sure. Yeah, okay.
Let's go terminal. Sure. That works. But yeah, that's the way we can multiply complex numbers. All right. Then example 6. Same thing. 24 over 8. Okay, yes, there's degrees. Kind of lied. Yes, we sometimes use degrees here, but we still want to stick with range for the most part. Because now we're dividing. If you were to go through the derivation, you'd see that. So I'm doing 3 at minus 75 now. What quadrant is that in, guys? And that's gonna be negative root 2 over 2. So you should get negative 3 root 2 over 2 minus 3 root 2 over 2i. And that's how you divide them. Okay, yeah, I'm really not going to do powers and roots today. That's not going to happen. So we'll save that for plus 1, 2, 3. Yeah, I could totally get this done in under a half hour on Monday. So homework can be slightly adjusted. So I apologize for not putting the homework last time. Homework for this particular stuff we just did. I think I'm going to assign you guys. Yeah, it'll be 1 through 6, guys. Just 1 through 6 of the other homework. So
I get my phone or my